Okay, improper integrals. So what are we doing here? Well, pause and copy. Trying to talk about a definite integral. Okay, usually we have like 1 to like 3, some function dx. Now one thing we want to do is say, well, what if we replace that 3 with like an infinity? And we have this infinite interval to consider. So we're going to call integrals of this form improper integrals. So geometrically, we could look at this example where we have 1 over x squared, and we're trying to find the area under this curve from 1 all the way to infinity. Now, in some sense, this is infinite, right? It looks infinitely long, this area. But does the actual area end up being infinite? That is a open question at this point. Okay, so we'll do an integral from 1 to infinity of this thing, and we will proceed in a specific manner. So here's our integral. You can pause and copy all this right now. So what we're doing is we are taking this area that seems to be in some sense, infinitely long, and we're going to replace it with a finite integral, a finite interval, 1 to b. Okay, so instead of going from 1 to infinity, we'll go from just 1 to some number b that's bigger than 1, but it's a number. Okay, and we'll find that value. And then once we've done that, we will let b go to infinity. Okay, so you can imagine this b moving to the right. Okay, so hopefully you kind of agree with this strategy, or at least it makes some sense to you. But the key element is to introduce this limit, which I'm going to insist you do on your very first step in all of these examples, exercises, problems, whatever. Okay, so what do? I start by calculating this integral here, just pretending the limit is not there. Just focus on this red rectangle. So pause and copy if you haven't done so already. So calculating this red rectangle, I get this. Okay, still no limit yet. I use my fundamental theorem of calculus. Double negative gives me a plus here. Now, finally, I can take the limit. You'll notice I don't write anything. I don't always write something, but maybe it's useful to put it here. So b is going to infinity. So this term is going to 0, leaving me with just this term. So I get 1. So what are we saying? We are saying that this area here is 1. 1 unit. So if this is 1 centimeter, and this is 1 centimeter, then this would be 1 centimeter squared. That lies under this curve between 1 and infinity. Now, in this case, we got a number. Okay, we did our improper integral, and we came up with a number, a real number. So this is what we call a convergent. We call this improper integral convergent. Now, again, if you get a number, your improper integral is convergent. If you have any other scenario, infinity, minus infinity, or just doesn't exist, we call that divergent. So I will repeat this later in writing, but repetition is good. Okay, let's do another example. Improper integral 1 to infinity of 1 over x. So same thing. First step, introduce a limit. Okay, again, you can kind of figure out the answer in these questions often, without introducing a limit. I am not going to allow you to do that. You must introduce a limit. If you do not put a limit in, you will get at most half of the marks. So I introduce a limit, then I work out my finite definite integral here, which gives me this after applying the fundamental theorem of calculus. Now the last thing I do is apply the limit. Now limit is b goes to infinity. So I kind of have ln of infinity here, which I need to remember is infinity. Okay, ln is a function that grows without a ceiling. So I got plus infinity here. So you could put plus infinity here if you want. Okay, but I want you to write down the word divergent. Okay, so again, because we got a number above that was convergent, infinity is not a number. So this is a divergent improper integral. Okay, a definition. So pause and copy all this, and I'll say some brilliant things about it. Pause, copy, pause, copy, pause, copy. Okay, so this is what we talked about before, introducing a limit. If you have a minus infinity, then you just go the other way. A is going to minus infinity. Here's an example of what that would look like. So what are we doing? In this case, you're maybe fixing an a here, finding this area, and then letting a move to the left. Okay, we're going to insist that f be continuous. This is not necessary, but things get a bit messy otherwise, so we're going to just stick to the not so messy situations. And again, convergent versus divergent. Okay, convergent is when you get a number, a real number. It could be 0, could be a negative number, could be plus 36. And divergent is any other situation. So often that's infinity or minus infinity, but it could be something else. It could be something like, well, if you think about whatever, pi to infinity of something like sine of x dx. This is divergent, but it's not infinity or minus infinity, if you think about it. Okay, you can't reasonably assign a number to this. So it's divergent. Okay, next example. Down here on the left, x e to the x. Okay, we're going to do by parts to start with. So I will do that separately in my green box here. This is pretty routine. You can pause and copy that. So I do that separately, and then I just plug it in right here. So again, first step, I want to, my first equal sign has got to be introducing a limit. Then I plug in my antiderivative, which I found here. I don't need the plus c. Okay, use the 0 and the a. And then clean things up a little bit. Distribute the limit across. And then say, hold your horses. Hold your horses. What is happening here? Well, this is of the form minus infinity dot 0. So I need my friend L'Hopital. Okay, so I'm going to need L'Hopital to evaluate that limit in the middle. The other two are no problemo. Okay, you may want to, e to the minus infinity. You may want to, maybe worth memorizing. This is not to be written down explicitly. It's in a thought cloud, but it's worth keeping in mind. Okay, where was I? That middle limit requires L'Hopital, which I do in blue here. Okay, this is one where I have to pull the exponential underneath. Okay, so coming back to my green, the first limit, which is -1. The last limit is 0. That was my thought cloud over here. And then the middle limit I found to be 0 in blue. Okay, I got -1, so that means convergent in this case. So again, I got a real number, so convergent.